In this pod, we'll investigate the reflection of light across different types of surface, as well as the refraction of light through different substances. Before you begin, you need to be familiar with some ideas about reflection. Let's look at some basics together.
You should know that in a plane mirror, a mirror with a flat surface, the image is the same way up as the object. It appears to be as far behind the mirror as the object is in front of the mirror.
Images are either real or virtual. A real image is one that can be caught on a screen, but a virtual image can't be. If you look at yourself in a mirror, the image you see is a virtual one. The normal is perpendicular to the reflector and is a line drawn at 90 degrees to the mirror. The angle of reflection is equal to the angle of incidence.
On a smooth surface, such as the glass on a mirror, all reflected rays leave at the same angle that the incident rays hit the mirror, so you get a clear image. This is called a specular image. On a rough surface, the reflected rays leave at lots of different angles, giving a distorted, unclear image. This is called a diffuse image. You can test this using a bowl of clear water. If you look into the still water, you will get a specular image. If you make ripples in the water, the image will become distorted and form a diffuse image.
Next, you can look at mirrors with curved surfaces. These are either concave or convex. How can you remember which is which? It might help if you think of a concave mirror as like the inside of a cave, and so is curved inwards. This means that a convex mirror is curved outwards. Let's begin by looking at convex mirrors. The image formed by a convex mirror is smaller than the object. It is upright and virtual, meaning it cannot be projected onto a screen.
Now let's look at concave mirrors. If the object is further away from a concave mirror than the focal length, then the image formed is always inverted, meaning that it's upside down. Its size depends on where the object is placed. Outside the center of curvature, the image is diminished and so is smaller than the object. But if the object is between C and F, the image is enlarged. All these images are real, which means they can be projected onto a screen. Inside F, the image is upright, enlarged, and virtual.
If you have a convex mirror and a concave mirror, you can test this by moving the object different distances from the mirror. You can do it at home using a polished spoon if you do not have any mirrors. The outside of the spoon is a convex mirror, and the inside is a concave mirror.
White light is made up of all the colors of the rainbow, or spectra. To test this, you can shine a beam of white light at an angle onto an equilateral triangular prism. Hold a sheet of white paper on the other side of the prism, and you will see rainbow colors, the colors of the light spectrum. This shows that white light is a combination of all the colors.
When white light shines on an object with a colored surface, the object will only reflect that color. All the rest of the colors will have been absorbed by the surface. For example, a red object absorbs all the colors except red. The red light is reflected into our eyes, which makes it appear to have a red color.
Next, let's look at refraction. When light goes from air to an optically denser material such as glass or water, the light will slow down. If the light beam enters at an angle to the normal, it will also change direction.
To investigate this, you need a ray box lamp and a glass block. Place the equipment on a sheet of white paper. Direct a light beam from the lamp to the glass block at an angle. Notice that the ray will bend towards the normal when it enters the glass block, and then bend away from the normal when it leaves the block.
Draw the positions of the rays on the paper and measure the angle of incidence, the angle of reflection, and the angle of refraction. Make sure that you understand the difference between reflection and refraction. The words are similar, but the processes are very different. You can repeat this experiment using blocks of different transparent materials, including water.
Finally, let's consider total internal reflection. You can explore internal reflection using a semicircular glass block. Start with the light ray A in the diagram, which is directed through the curved edge of the glass at around 25 degrees to a normal drawn at the middle of the straight edge.
Light ray A will leave the block through the straight edge. Because it is leaving the glass and entering air, it will bend away from the normal. This is refraction. If you keep increasing the angle to position B, the light ray does not leave the block through the straight edge. The angle that B makes with the normal is called the critical angle. If you keep increasing the angle to position C, all the light is reflected back into the glass. This is called total internal reflection and is the basis on which optical fibers work.